Dear students, today we are going to discuss about convex sets and convex functions. We are starting our journey in the study of convexity, a concept extremely important for both economics and optimization, and many other areas like engineering, management, business, and so on and so forth. Convex set is a set with a very simple and very special structure. It tells you that if you take any 2 points in that set and join them by a line segment, a line, that is a line segment joining those 2 points, that whole line segment would lie inside that set. Means in that zone, you can go from a point A to a point B by walking straight from point A to point B along a straight line. So formally it means that given any 2 points x, y and c, and whatever lambda you choose in 0, 1, lambda y plus 1 minus lambda x would be an element of C. So when we move the value of lambda from 0 to 1, as I told you earlier, we are moving from x to y. So I've given a figure of a convex set and deliberately took away the figure of the non-convex set, because I want you to think about a very important example of a non-convex set, and that example is you yourself. We human beings are non-convex sets in R3 in 3 dimensions, because if you take a point on your head and a point on your shoulder and join them, then except those 2 points, rest of the points on the line segment are completely out of your body. So your body, our body, we human beings, our body is not a convex set. But convex set, by the way, is very important. As I told you, this would play a very important role as we go on. So related with the convex set is the 2 types of functions, convex functions and concave functions. Convex functions is used for minimization, concave functions is important for maximization. So you take any convex set C in Rn, and the convex function is a function which satisfies the following fact, that if you take any x, y in C, then the functional value at any convex combination of these 2 points, so when a point is combined in this form, lambda y plus 1 minus lambda x, this is called a convex combination of the 2 points x and y. So if you take the functional value of any point on the line segment joining x, y, that would be less than the convex combination of fy and fx. So any 2 points, when we are combining it with 2 real numbers, you are making a linear combination with 2 real numbers which sum up to 1, and the values are lying between 0 and 1, and such combination is called a convex combination, not a linear combination. It's a special type of linear combination. So when concavity of a function is same as telling that minus f is convex. Concavity is the same thing but with the inequality reversed, and this is used in maximization. Now we will simply get into the key issue as to why these class of functions are very important in optimization. We will just talk about maximization just to keep economists happy, and then we will give as a problem the story, the minimization story, which you can try out because the arguments are similar. So let us consider a convex set U and a concave function from U to R, which we call f, and we consider the problem of maximizing the function f over a convex set C which lies inside the convex set U, a subset. Then the key thing that makes concavity and convexity of functions so important in optimization is that every local maximizer is a global maximizer. So local maximizers are not there, they are all global maximizers. If you do not have convex functions, then we talk about local maximizers. We have been speaking about local maximizers, local minimizers when we were linking derivatives with optimization, but such a link is really not required, that you have to separate local minimizers and global maximizers and local maximizers when you are maximizing concave functions over convex sets. So this becomes very important in application, because in economics we are always talking about maximization problems, while in engineering or finance or management we are talking about minimization problems. where convexity plays a role, because in that case you will be able to show that every local minimizer is a global minimizer. So here let us start proving what we had just said. So let x star element of C be the local minimizer, and so you know what it means, that you will around x star you will get a ball, you will be able to find a delta such that you can draw a ball of radius delta. Just do the take it on a paper, just take a convex set C, take on the boundary a set x, and just draw a ball of some radius delta around it. So some part of the ball would intersect inside the intersect the set C, and some part won't intersect the set C. So you know the part in which it intersects the set C, we must have fx less than fx star. So there must be a delta for which this happens, that for all x in this intersection zone this must happen. Now what we are going to show, that if I take any y outside that zone, this intersected zone, I will still be able to show for those y's also fy would be less than fx star. This is the key point. So means for the intersected zone I have shown, and I am going to show it for any other zone, and any other point. Go to any other zone of the set, take any point, take the functional value, it will be less than fx star. So hence we will have a global minimizer. So x star would become a global minimizer. So how would I show that? So now because this is a convex set, I can join y with x star. Okay? Because it is a convex set, I will join y with x star. Now what would happen? Now what is happening? I am joining y with x star. So if I move from x star towards y, I am taking lambda from 0 to 1. But if I move from y to x star, I am bringing down lambda from 1 to 0. Now then, as we move from y towards x star, as we walk towards x star, after walking for some time, we will be suddenly coming inside this zone. Obviously, you can just draw it and check it out. So it is clear that for all that there would be a threshold point z lambda naught, there will be a threshold point lambda naught, such that for all lambda lying between 0 and lambda naught, these points on the line segment joining y and x star would come inside this zone. It's a very simple thing to do. I think I should have given a figure. Okay, I'll put a figure when I send you the notes. So this is quite an important idea, that okay, you have started walking from y, you are coming towards x star, but you know that there is an intersected zone already around x star. A part of the ball has intersected, because the x star is the center of the ball, a part of the ball has intersected the set C, so that zone is there. So x star is lying in that zone, so x star is interior of the ball, so which is inside the ball, is the interior point of the ball. So some part of the line segment is within that zone. So as you start walking, it means you reduce the value of lambda from 1 to 0, you actually, there is a point beyond which you come inside that zone, and that is what I have written. Once you have done that, you know that by concavity of f, so for any lambda between 0 to lambda naught, I'll have this result. Now, because for any lambda from 0 to lambda naught, I have z lambda inside this, and by the definition of local maximization, I have this inequality true, that fx star must be greater than or equal to fz lambda, which means this here I will put, from this inequality I will put this to be greater than fx star, and then I'll cancel out one fx star from this side, this fx star, and so I'll have lambda fy minus fx star less than equal to 0. But because lambda is strictly greater than 0, I can divide both sides by lambda. So what I have done, for as y is arbitrarily chosen, we have fy is less than equal to fx star for all y which is outside this this intersection zone. And anyway, we also have fy less than fx star for all y here. So which means fy is less than equal to fx star for all y in C, and hence x star is a global maximizer. Now comes a very important result. This result, which we will call the minimum principle, has a quite similar sounding name of a result in complex analysis. Actually, if you do not know the history, there is a famous book called Convex Analysis by R.T. Rockefeller, who is one of the legends of optimization and convexity. So Rockefeller, as a postdoctoral student, was giving this set of lectures to students in Princeton, and he was also discussing these things with Tucker of the famous Kuhn-Tucker conditions, which we will learn in the coming few days. And he had asked Tucker what should be the name of this collection of this lecture notes, because Tucker wanted that this could be printed as a book. So rhyming it with complex analysis, Tucker told it, let us call it convex analysis, and the name stuck on. And this is called the minimum principle. The minimum principle means what is the behavior of a global minimum of a concave function. A concave function may have a global minimum. A local minimum may not be global, but it may have a global minimum. It says that if U be a convex subset of Rn with a non-empty interior, and there are interior, non-empty interior means there are interior points. So it's kind of a closed set, possibly a set with a boundary and everything inside. So consider a concave function and assume that it achieves the global minimum value at an interior point of view. If it does so, then f is constant on U. This is a result. This kind of similar result is there in complex analysis. And that is true for analytic functions, and that you can go and seek out in the net, or look into any book on complex analysis, and you will have that. So what is there? So it says that let the function achieve its global minimum at x0 element of U, which is an interior point, and that is not x, x0 is an interior point. Suppose on the contrary we assume that f is not constant on U, then there must be an x, right? Because so if it is constant means fx naught is equal to fx for all x, but because x naught is the minimizer, fx naught is less than equal to fx, but because the function is not constant, there must be one x at least for which fx is strictly bigger than fx naught. Now what is the meaning of an interior point? That if from x naught, if you move a very little bit, you can always move a very little bit and still stay in the set. That is, there will be a ball around that set, open ball, which lies inside the set. That is the meaning of interior point. Means you can always find an open ball with a given radius which will lie with an open ball centering at that point x naught, such that that whole ball would lie in the set. Now it means that I can move along any direction, whatever direction I move, doesn't matter the direction. If I move along very little, that is, I'll move from x0 to x0 plus lambda w, say w is a vector and lambda greater than 0, the scaling. So if I move a little bit, lambda could be very, very small, I will still remain inside the set. When I can have a threshold lambda within which I will remain inside the set. So look at let's set w equal to x0 minus x. Then this y x naught plus lambda x naught minus u is actually element of int u, actually means interior of u. It will actually, we can show that it will lie in the interior of u, that is within the collection of all interior points of u. It doesn't matter, you can just write by very definition, it means y should be in u, that's it. That interior point means the whole ball should lie within u. So this such point should lie within u. So you can find the lambda sufficiently small, very near 0. So obviously I can choose lambda between 0 and 1. Once I do that, please understand this is not a convex combination, because this means 1 plus lambda x naught minus lambda x. This is not a convex combination. So this is in u. In fact, you can choose it to be in interior of u. Interior of u actually is an open set. And you know what is an open set. The collection of all interior points of a set is an open set because all the points there are interior points. Hence, now by doing a little algebra, we can write x naught as 1 by 1 plus lambda divided by 1 plus lambda x. Now this one is a convex combination. Now applying the concavity, f of x naught is greater than equal to 1 by 1 plus lambda fy plus lambda by 1 plus lambda. There is a mistake here, I am sorry. It's lambda by 1 plus lambda fx. There's a mistake, please. So you basically apply concavity here. F of x naught is greater than equal to 1 by 1 plus lambda fy plus lambda by 1 plus lambda fx. Now fy anyway is greater than or equal to fx naught, because x naught is the minimizer. Fx is strictly bigger than fx naught. So here we will have a strict inequality, thus proving that fx naught is strictly bigger than fx naught, which is a contradiction. So at the end of this talk, I ask you to do a problem as a homework. So for a convex set f, which has to be minimized over, for a convex function f, which has to be minimized over a convex set, every local minimizer is global. What about a local maximizer of a convex function? Is it also a global maximizer? So you have to just think about it. Show that for a concave function, every local minimizer need not be global. And now you can, for the convex function, you can similarly develop what you can call as the maximum principle. So you also try to figure out the maximum principle for convex functions. So with this, I will end my talk. Please forgive me for this mistake. This will be corrected. So thank you very much. I would be happy to have any questions. Thank you.